Kinematics studies the motion of a particle but without answering the question how the motion came about. Kinematics, as a part of mechanics, as a part of physics, wants to describe motion in such a way that we know the position of a particle at any moment. Knowing that, or knowing the position of a particle at any given moment, we also know how fast a particle changes its position. How? We can know such a thing by comparing two positions in two different moments. We can also know if it changes its velocity during motion, which is the acceleration of a particle. So it seems that all we need to know to describe motion is to know the mathematical dependence of the position of a particle on time. Here I will describe a one-dimensional motion. This kind of motion is very important because others, more complicated motions in 2 or 3 dimensions, can be observed as 2 or 3 one-dimensional motions. Namely, each position vector, in general case, depends on the 3 coordinates x, y, and z. So if the coordinates x, y, and z depend on time, we can observe each coordinate as a single one-dimensional motion. Thus, the 3-dimensional motion can be observed as 3 one-dimensional motions. Okay, now if we want to describe some motion in one dimension, or maybe it's easier to talk about moving in a straight line, we need to know how the position of a particle changes over time. First, let's see how to determine the position of a particle at a specific moment. Let's look at the position of this particle, for example. How would you describe where this particle is located? Maybe to the left, near the end of the screen. Yes, but of course this is imprecise. Or this, maybe to the right, near the end of the screen, but closer than it was the one on the left side. What can you say for this one? Or this one? Problem, yes. But I think it's easier to do the next thing. We will choose a position on the straight line and then compare the positions of all other particles with respect to that position. This position is called 0 point. This one is an example of 0 point. So now for any position of a particle, we can say that it is either on the left side of the 0 point or on its right. For example, white, green, and red are on the left, and red, blue, and yellow are on the right. We can also determine how far the particles are from the 0 point. However, if we look at the 2 red particles, we can see that they are equally away from the 0 point. One is on the left and the other is on the right. How can we avoid this left-right side? By imposing that one side of the line to be negative and the other to be positive. So, from the given straight line, we will make an oriented number axis. Everything about axis is a matter of our choice, selection of positive and negative side, and 0 point. So, we determine the position of a particle relative to the 0 point in a way to determine whether is it at the positive or negative side and how far away is it from 0 point. All this leads us to vectors, of course. As can be seen, for each particle we can define a vector started at the 0 point and ends at the point where the particle is located. Now, regardless to the fact that 2 reds are equally distant from the 0 point, we can use the vectors to distinguish these 2 particles because they are on different sides of the 0 point. Okay, now let's look at some of the motions along the straight line. Consider these 4 particles. In general case, they do not have to start from a 0 point, but from some place away from it. Here we have chosen that the 0 point is at the beginning of the board and that the positive side is the one on the right. So no matter how the motion came about, let's observe the motion of these 4 particles. What do we need in order to describe the motion of these particles? Again, we need to know the time dependence of the position of the particle. Then what to do? Well, first of all, we need to determine the position of a particle at the beginning of the motion and the position of the particle at the end of the motion. The position of the particle at the beginning of the motion is determined by the white vector. With the green vector, we will denote the position of the particle in the final position. With those 2 vectors, we are able to define a new one, so-called displacement vector, as follows. A white vector represents an initial position, green one final position, and the red one is displacement. So, displacement is equal to final position minus initial position. In some point, we will define distance, which will be represented by the blue line. Now, let's look at the motions of particles and determine their displacements. If we look at the green and red particles, we will have very similar situations. We can see white, green and red vector, and of course red or displacement is equal to green or final position minus white or initial position. But what about the blue and the yellow one? We can see that something is missing. For blue particle, it is a green vector or final position, and for yellow particle, it is displacement or red vector. Actually, nothing is missing. Here you can see that the final position of the blue particle is 0 vector. And here you can see that for the yellow particle, displacement is 0 vector. But no matter how strange as it may sound, the displacement is 0 because of the definition. Displacement is equal to the final minus initial. And you can see that in case of yellow particle, green is equal to white one, and differences between them is 0, of course. But here is something that it's not 0. It is distance, mentioned earlier. So let's say something about distance, and we will see what makes the difference between distance and displacement. Of course, the main difference is that displacement is vector, and distance is not. But nevertheless, let's look at the green particle again. The blue line represents the distance traveled by this particle. Nothing spectacular. And obviously, the blue line and the red vector are the same in length. Then, let's look at the red particle. Again, the similar situation as for the green particle. Blue line is the same length as the length of red vector. However, in the case of the blue particle, something else happens. The blue particle firstly moves in a positive direction to the end of the board and then in the negative direction to the other end of the board. It's obvious that the length of the blue line, or more precisely the blue lines, are not equal to the length of the red vector. In this case, there is a pretty clear difference between distance and displacement. And again, apparently the weirdest part is with the yellow particle. For the yellow particle, we saw that displacement was 0. But the distance, as you can see, is not. This will be enough explanation for the introduction. Now I will show you how to use these 1D motions to describe, for example, 3D motion. This is a part of another video explaining motions in 3D. So here you can see that the motion in space can be represented with three 1D motions. However, at this point it is more important for us to determine how fast are particles and what is the difference between average velocity and average speed. For this reason, let us again observe the motions of four particles. In this case, for simplicity, let each particle start from the 0 point and the positive part is at the right. In this case, the initial position is 0 vector. Thus, the displacement or final minus initial position will be equal to the final position. Here are four different motions that help us understand most of the one-dimensional motions. It should be noted that the particles start and stop at the same time. The duration of motion of all four particles is equal. Currently, you are looking at the final positions of all four particles. Pay attention to the red and the blue particle. For now, just notice that both particles have the same starting and ending points. Now, after all that we learned, it's very simple for us to imagine displacements of these particles. Nevertheless, let's repeat. Displacement is equal to the final position minus the initial position. Also, let's repeat that the initial position is 0 vector. Again, red vectors represents the displacements for each individual particle. But the green vectors are not initial position. Remember, initial position in this case is 0 vector. Now, using displacement, we can define the average velocity. It is a vector equal to displacement over elapsed time. But let's look at the genesis of the red vectors. For the green and the red particle, it is quite simple. However, if you look at the blue and the yellow particle, you can see that their motions should be described as two consecutive motions. Now, let's calculate the average velocity for these four particles if the length of the board is 24 meters and the movement of each particle lasts 10 seconds. Look at the green particle. Pretty simple. The particle was moving 24 meters in a positive direction. That's why you have plus 24 meters in the numerator. The vector I is, of course, the unit vector of the x-axis. So the average velocity is plus 2.4 meter per second. Look at the red particle now. Again, quite simple. Displacement is plus 12 meters, and of course, average velocity is plus 1.2 meters per second. Now, when we look at the blue particle, we can have a problem if we don't understand the terms displacement and average velocity. Although the motion of the blue particle is different from the motion of the red particle, their average velocities must be the same because they have the same initial and final position. This is also shown in the calculation for average velocities those two particles. In the numerator, for the blue particle, does not need to stand plus 24 minus 12 meters at all. It is shown here only to see the difference in the motions between the blue and red particles. In the numerator should stand only plus 12 meters as it was for the red particle. And of course, again, something that can be confused. Of course, if we do not understand the concept of displacement and average velocity. So, we see that the average velocity of the yellow particle is 0. How can it be when we know that particle was moving? Well, simply because the displacement is 0 vector, and the average velocity is defined like displacement over elapsed time. That's the point of the definition of the average velocity. That's the rule. However, in order to fully describe the motion of a particle, it is necessary to define another quantity called average speed. Unlike average velocity, in the case of average speed, we need to know the distance traveled by a particle. Unlike displacement, distance is not a vector. Let's look at the distance for these 4 particles. According to what we see, the green particle has an average speed of 2.4 meters per second. The red particle has an average speed equal to 1.2 meters per second. The blue particle firstly crosses 24 meters and then 12 meters, all in 10 seconds. Therefore, an average speed is 3.6 meters per second. When it comes to the yellow particle, we can see that it goes twice 24 meters in 10 seconds, which of course represents a speed of 4.8 meters per second. Let's compare the average velocity and average speed for the red and the blue particle. Average velocities, these 2 particles, were equal to plus 1.2 meters per second. In the case of average speed, we see that those values are not the same. After all, I hope that you know the difference between displacement and distance, and of course between average velocity and average speed.